Pre-calculus 1.6. Today's lesson is about shifting graphs, shifting, reflecting, and stretching graphs. Graphs of many functions are transformations of the graphs of the basic functions. Yesterday's lesson we learned about the basic or the common function, also called a parent function. They were just simply x squared. That would be the common function. And today we're going to learn how to shift that graph of x squared and how to see that the graph of x squared plus 3 is simply the graph of x squared lifted up 3 units on the y-axis. The graph of negative x squared is the reflection of the graph of x squared in the x-axis. So here, if we had x squared plus 3, we take this plus 3, we count up 3, we move the vertex, and if we had a couple other points, we'd move those, we'd connect them, we'd draw our smooth curve up there. This plus 3 moves the graph, it shifts it on the y-axis. Now we're going to see that that's different than if we had the plus 3 in the parentheses. Inside of what I'm going to call the function operator is going to be a left and right shift. Outside of this function operator is going to be an up or a down shift. And you could see this if you made a table of values for points on this graph. You could see that the y's were always 3 more. Let's look at another example. Actually generalize. The graph f of x plus c shifts the graph y equals f of x c units on the y-axis. F of x, if this was f of x, then f of x plus c would be this one. Shifted downward c units would be if it had f of x minus c. Then we would shift down. Okay, example. Use the graph of f of x equals the absolute value of x to graph the absolute value of x plus 3 and the absolute value of x minus 4. So here's our common function, or our parent function, of f of x equals the absolute value of x. And so if we're adding 3 to this, we're going to see it's going to be shifted up and the vertex is going to be here. If we subtract 4 from this, we're going to see it's shifted down and the vertex is here. We go down 4 units. And we can pretty much shift any graph this way. So if we know what the common graph looks like, then we can find the graph of something adding or subtracting from that. So sketch the graphs given by x squared plus 1, and so on. You do this on your calculator, you'll see exactly this, if you were to enter all 3 of these graphs. So here's x squared plus 1, x squared minus 3. Okay, so now, looking at this other way, if the number that we're adding or subtracting is inside with x, now we're going to see how it shifts left to right. So if we had this graph, f of x, and it looked like this, and instead we did minus some number c, inside of those parentheses there, it moves it to the right. Now this is going to seem like it's moving the opposite way that it should. Okay, and we'll go over that in later lessons why. If it's minus c, it's going right. If it's plus, it's going left. Okay, so let's look at a real example. X to the third. That's our common function. And now we're going to look at x minus 2 to the third. You see how the minus 2 is inside that. It doesn't say g of x equals x to the third minus 2, because this is a move downward. It's not inside of this function operator. This would move it downward. But since it is inside of the cubing function, the function operator, this is going to move to the right 2 units. This one, since it's a plus, it's going, and it's inside, it's going to move to the left 2 units. So let's look at the common graph. There's what x cubed looks like. And if we wanted to graph x minus 2, we would just take every point on this and move it to the right 2 units. So the vertex would move to 2 units. Each point would move 2 units. And we'd see g of x equals x minus 2 cubed. Just this graph moved over 2 units. Now if we moved it plus 4 inside, we're going to move it 4 units this way. So this vertex here is going to be right through there. Let's look at another example. X squared. X squared minus 3 and x plus 1. Again, inside the squaring. If it was this minus 3 moves up or down. Here it would be down. Because it's inside of the squaring. See here, here's your squaring. Because we've moved it inside that, now it determines left or right. And you can see each of these. The center one, of course, is x squared. One moves this way is the one with the plus. One moves that way is the one with the minus. Take a look at the graph of the function where y equals x plus 5 minus 4. Now we have both movements at the same time that are going to happen. Okay, notice outside we have a minus 4, so it's going to shift the graph down 4 units on the y-axis. Inside we have this plus 5, which means it's going to shift the graph 5 units to the left. So here's our parent function, or our common function. And so we're going to take this point, and it's going to end up shifting down 4 and over 5. And you can take this point, and it's going to shift down 4 and over 5. And you can see when we graph that, we can make that vertical shift, downward 4, and then we're going to make the 5 back. And here would be our new graph. So we shifted down 4 and back 5. Down 4, and then we take this and shift it back 5. And here's the graph of the square root of x plus 5 minus 4. We tend to want to think this is making it harder. It really makes it pretty easy. You can look at a graph and you know how to read it, and you know what its equation is just from looking at it without doing any math. It saves you a lot of time when you have to do things that are depending on knowing that information. So, just basically a reflection. When we talk about negative x, well, if these are positive x's, negative x's are over here. And when you change what's inside of the function operator and make it negative, it's going to reflect it across the y-axis. Reflect it over the y-axis. Okay? Because if you're changing what was positive and you're making it negative, that's now taking it, same thing that was here, and it's putting it over here instead. And if you take the negative of the whole function, see the difference? This is the negative of the input. It flips it over the y. If you take the negative of the output, it's going to flip it over the x-axis. Example. Negative x plus 3 squared, using the graph of f of x. Oops, I went backwards somehow. Hang on one second. Okay, so we have a shift, 3 units left, and we have a reflection. And since the x isn't negative, but the whole thing is negative, the whole thing, this is going to reflect over the x-axis. The whole thing, the whole function is negative. So we begin with x squared. We take x squared and we reflect it across the x-axis. And then we take our reflection and we shift the graph 3 units to the left. The negative f of x flips it. The plus 3 moves it. At this point, I'd usually ask if you had any questions, but now finally, the last thing is if we have some number multiplying f of x. This is going to stretch it. It's going to stretch our graph. For example, and if c is a fraction, that's what this means. It's greater than 0 and less than 1. If we multiply it by a fraction, then it's going to tend to squash our graph. They say shrunk vertically. Squashed, make it look short and fat, kind of like me. If you laughed at that, stay after school today. Example, y equals 2x squared is going to be the graph of y equals x squared stretched vertically by a factor of 2. So it's going to look taller and narrower than x squared. For example, there's x squared. There's 2x squared. Well, why? Why is that? Well, because if x squared is 4, 2x squared is 8. So instead of having 2 comma 4, you have 2 comma 8, because you're doubling it. So it's going up much quicker. It's increasing at a much increasing rate, a much rapider rate. And so it's going to be narrower, and it's going to look like we actually took it and stretched it. Now y equals 1/4 x squared is the graph of x squared squashed. I say squashed, they say shrunk vertically by 1/4. It's going to look, see, wider, 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 kind of like I've been getting wider for the last 10 years. Example, again, y equals the absolute value of 2x. It's the graph of the absolute value function. So if you learned yesterday's lesson and you know what absolute value looks like, it looks like a v that's symmetric to the y-axis, who has its vertex at the origin. We see we're not adding or subtracting inside, so it doesn't move left or right. We're not adding or subtracting outside, so it doesn't move up or down, but we are multiplying by 2. So what that does, again, is it stretches our graph. It's not as short and stubby as it used to be. Now again, if we multiply by 1/2, if we multiply by less than 1, here we by more than 1, it makes it tall and stretchy looking. Here it's going to squash it, it's going to make it open, it's going to be wider. And that's exactly what you see when you look at it. Sketch the graphs. X cubed. And again we see x cubed. We see 10x cubed, much steeper, stretched. We see 1/10 x cubed. It's like it's stretched wider. 10x cubed, it's like it's stretched taller. 1/10 x cubed, like it's stretched wider. Now we put all 3 ideas together that we've learned today, and we are going to have an upward shift of 3. We're going to have a shift left of 1, and we're going to squash our graph or stretch it wider. Okay? We begin with the graph of x cubed. We all learned what that looks like yesterday. Okay, and we're going to do one transformation at a time. Here's our graph of x cubed. We move it 1 to the left. Then we have to move it up 3. Oh, well, they've stretched it first. Doesn't matter our order. Doesn't matter our order. So they've stretched it first. Now look, it's a little bit wider than it was. And now we go up 3. And there's the graph. So we start with x cubed. We move it left 1. We stretch it 1/2. We move it up 3. And realistically, I understand why they did the order they did, and they did it right. They started at the inside, and they worked their way out, kind of like peeling an onion to get to the outer layer. They started at the inside. They did the +1 first, then they did the stretch, and then they did the up 3. That's it. Thank you.